Good morning, good evening, good afternoon, wherever you are, whatever time of day it is for you. I hope that you are tolerating the fact that we are going to be not meeting in person and you will be watching this video at your own leisure, at your own time. Hope that works well for you. This is officially spring break at Oklahoma Christian, but in the grad level program, we can meet during the week, quote unquote, meet. And I've decided to go ahead and press on. So I'm going to record this lecture for you. This is week 2. And good news for you, because we're not meeting in person, I will not be giving a quiz. So we simply will drop that quiz from our curriculum this semester. And that means 10 points less that you cannot get. And that's fine. It won't be the end of the world. This week's lecture and topics that we're going to study are singleton, adapter, command, and facade. Now the last three, the adapter, command, and facade, as you'll see, are somewhat related. And the singleton class is kind of unique. The singleton class is when we want to have a situation where we've got a program and maybe that program is controlling something, like maybe a light switch for a very simple thing, or maybe it's controlling how packets are sent in and out of a router or something like that. But in any case, whatever that job of that one class is, we only want one object in the entire system. We don't want to have the possibility of having more than one object instantiated. And so here's our little picture we see on the left. And I'm going to see if I can find the, there it is right there. This is the laser pointer. There it is. Okay, good deal. So over here on the left, we've got a class of some kind, and we're instantiating a lot of different copies of that class. This is what we don't want in the singleton. What we want in the singleton is Tigger on the right. Tigger is, for those of you who do not know, Tigger is a classic Disney character. Winnie the Pooh is the story that Tigger appears in, and Tigger's famous line is, "I'm the only one." That is the story of our singleton class as well. So let's take a quick look at singleton here. Oop, I got to turn the laser off to make this work. There we go. I'm going to put the laser back on so I can point with it. All right. So the singleton class is very, very simple. You're going to be quite happy with how easy it is to create singletons, but it does come with a few provisos, limitations, warnings. There are a lot of times when we only need one object in something. And a good example is, let's say you have an object that is responsible for assigning identification numbers to other things, and you don't want that to be duplicated, because if you had two objects, they could be out of sync with each other, and each one be assigning unique numbers, but they only have their own set of unique numbers, and because there's two of them, now you have two copies of every number, and whatever it was you were doing with that is broken. Or you may have an object that controls access to a physical device, as I referred to earlier. It could be something where you are controlling a light switch or controlling a power lockout. I'm going to have that as an example here in just a little bit. And you can't afford to have two different objects that control the power lockout, because that could be very unsafe for whoever's working on the power switch. So we're looking at a situation where if you instantiated or made two objects from the same class, the two of them could create serious safety or other synchronization issues. Now this sounds like you could just use a global class, a global variable, or maybe set up a static variable in a class. But singletons can do a little bit more than that. And when we use a singleton class, what we're really doing is using the convention for making certain that only one object is created from a given class. And it also gives us a global point of access, as you will see. It gives us a place for everything to go and say, hey, I need to talk to the singleton to ask it to do something for me. And if it's done right, it'll be thread safe. Now, there are some issues that we'll see if you don't do it right and you live in a threaded world. In other words, you can have multi-processors working at the same time. And it is very unlikely, but it is possible for the timing to be just right for two objects to be created at the same time. So we want our package, our singleton class, to be thread safe. Now, how would you create let's talk about, in Java, how would you create a singleton object? How would you create any object? Well, you say new my object. You say, hey, I want a new object of whatever it is. And the question on the left then says, well, if another object wanted to create one, couldn't it just call the new as well? Yes, the answer is yes. If something else wanted to create a second copy of my object, it would just call new again, and now you'd have a second one. And if you had a public constructor in a class, which is the default, Most people, until they come across the Singleton class, never even think about the possibility of having a private constructor. That just makes absolutely no sense at all, because why would you create a class with a private constructor? You wouldn't be able to call the constructor when you needed to, and that just seems completely stupid. So if you had a private constructor, no one would be able to get to it. What, well, except that the members of the class would be able to get to it, but if it was private, you wouldn't be able to create any members of the class, in other words, any objects. So how would we get around that? Well, it turns out there's kind of an interesting loophole. And this is the heart of the Singleton class. And this is, to me, this is really a wonderful, wonderful class. And I have used Singletons in many, many different applications. If you have a static method that's public, you can call the static method even if you don't have an object from the class. So if you have a static method, you could have the static method, which is inside the object, then get to the constructor class, which would be private, to create an object and return it to you. But here's the magic of the Singleton class. That static method, which would not be associated with any object and would be available even before any object was created, could prevent you from creating a second one. In other words, it could be kind of a gatekeeper to the constructor. And what we'll see is that the way it works is that we are going to have a static public method, and the static public method is going to be asked to get the pointer to the static, get the pointer to the one and only object that will be created. And the way it's going to be a gatekeeper is it's going to say, hey, if the object's already been created, I'll just return you the pointer to the objects, the reference to the object. But if the object hasn't been created, I'll go ahead and make one and then refer it to you. And you'll see how this works in a second. So here is the classic Singleton class. We have a Singleton, and this is our unique instance. Notice that this private static Singleton is creating a Singleton object. So it's creating an object. Well, it's not creating it yet. It's declaring that we will have a Singleton object, and it will be our unique instance. It'll be our one and only object in existence that is a Singleton type. Here is a private constructor. No one can call it from the outside, even though we might want to. And then here is the static method, and the static method's logic is so simple. This is such an elegant solution. If the unique instance is null, in other words, if I have not yet created this unique instance, I'll create it, and then I'll return it. So what happens if the unique instance has been created by some other part of the program that called this code? Well, if the unique instance is already there, I'll skip the creation part, and I'll just simply return the one unique instance. Now, I hope you'll read the chapter on Singleton because they provide some really, really good insights. But this is it. This is the heart of the Singleton class, and you can see how beautiful and elegant it is. Such a wonderful. Let's do an example here where we have a lockout. If you've ever seen or been a part of any kind of safety program in an industrial environment, you will know that when someone is going to go work on a part of any part of electrical system, that they will actually go and lock out. And the way it works is they go to the place where the power switches are, they turn the power off, and then they will close the cover of it, and they'll put their own personal lock on it. No one else can take that lock off. Then they'll walk over and work on it. And this prevents someone else from accidentally turning the power on because no one else has the key to the lock of the employee who's actually working on it. So that's what we have here. We simply have a situation where we want to turn the power off and no one else can turn it on. Well, if we have a class that can have two instances of the power controller, one power controller could think it's off and the other one could think it's on, and it would be a situation where you might have two employees who one of them turns it off, goes and works, the other comes in and turns it on because they both have the ability to do that. So what we're going to do is we're going to eventually create this to where this is a Singleton class. But first, our bad lockout here, we have two Booleans. Is the power on or off? Are we locked out or not? And here is the lockout method. If we are going to this is the lockout constructor. Here's the lockout. We initially say the power on is true. No one is locked out of the system. And then we have a method called lockout. This is when we want the power to be off and no one else can get to it. We say lockout is true and power on is off. And then we have a release lock method. Lockout is now false. This is when the employee's done and they're ready to take the lock off. Now here's what it takes to turn on the power. If we want to turn the power on, we check to see if it's locked out. If it's not locked out, we'll turn it on. But if the lockout is true from up here, that means someone's working in there and we don't want to do that. Well, this is not a good application here because if we had two copies of these, they could have their own copies of power on and lockout, which could lead to a catastrophic situation. So here is a kind of fill in the blank here for a singleton. We have a private Boolean, just like before. This is lockout and power on. All right, now what are we going to have here? Well, if we go back a page and look at the previous slide, we would see that this is where we put our instance, our private instance. So we're going to have a private lockout object, and the private lockout object is going to be the only one that's allowed. All right, so here is our constructor, just like before. But what are we going to do that's different with the constructor here? Instead of saying public void lockout, we're going to say private void lockout. Now no one can create this. And finally, what goes in the get instance class? This is the one that's actually going to get us a pointer or a reference to the only one lockout. Well, this is going to be that public lockout. It's going to return a lockout object. Public lockout get lockout or get instance. And in this method, it's going to be a simple if statement. If the lockout object, the one we created up here, is equal to null, create it and then return it. Else, just return it. And that's our lockout code. Looks very nice, very simple. There's the lockout. There's the private lockout. Now I left the void out here. You'll have to forgive me for that. And finally, here is the actual instance of the code. And if you're watching this on YouTube, you can simply pause it and look at that a little bit. Again, here's the fundamental structure of a singleton class. We have a private instance of our one lockout object that we're going to allow to be made. We have a private lockout constructor, and then we have a public static method that can be called even before the lockout object has been created to return it. And this guy just says, hey, if he hasn't been created, create it, then return it. Otherwise, if he has been created, just go ahead and return it. All right, so I mentioned this earlier. It's possible if you're in a threaded environment or a multi-process environment for two threads, two different processes to be running, and they both come to the if statement at exactly the same time, and they both get the answer that, hey, the object has not been created, and so then they both step in and create an object, and now you have two objects. And so what we want to do is we want to avoid a situation with multi-threading, creating two objects. And there are several ways we can do this. We could make the static method get instance synchronized. In other words, we could put a synchronization block around that entire method. And that is one way to do it, but that does put a significant amount of overhead around that block. And that block is going to be called all the time. Everybody who wants to get to the single object is going to have to go through that block. And if we synchronize it, we do put some extra overhead on. So there are some other possible solutions. If performance is not a concern, just go ahead and do that. Put a synchronization block around the entire get instance method. However, you could also use what's called an eagerly created method. And this is a situation where before you release the system to the users, in other words, when the system is booting, before you allow any user to log in or any action to be taken, in the early booting and the kind of self-construction of the internal objects of the system, you go ahead and create it first. So before you let anybody else create it, you create it, and you, I hate to say this, but you hope that there's no way that there was another process out there that created one. And usually you're going to be okay. So this is one possible solution where you simply create the one object before anything else can get there, and you remove the situation where two threads can run at the same time. The other thing you could do is use what's called a double check locking. And in the double check locking method, you're in that get instance method. And the first thing you do, you don't lock the entire get instance method. You simply say, hey, is the singleton object created? Does it exist right now? If it does, then the command that is going to create it, that is synchronized. And so you simply put the synchronization inside the if block. Now, if the object already exists, you'll skip over that synchronization and never encounter the overhead of it. So your get instance will be a very quick return. If, on the other hand, the instance has not been created, and this will only happen one time, then you'll synchronize the creation of it, and that will prevent two threads from coming to true at the same time. And so that will basically allow you to have a high performance but thread safe instance of the singleton. All right, so that is the singleton, and hopefully that is very clear to you. I think the singleton is a simple and beautiful but very powerful. I'm writing a little, it's a very, very simple little dungeon game for my grandkids. And one of the things that I needed in there was I needed to have a single object in the entire system. I didn't want to ever have more than one that represented the current room that the dungeon crawler player, the adventurer, is in. And so I created a singleton object, and then that object, I can always count on the fact that that object is referring to the single and one and only room that the player can be in. And so there are just tons and tons of different kinds of applications for the singleton object. And I think as you use it here and there, you will begin to find that it's very, very useful. All right, let's talk about another one. And here's another one. I just mentioned my little dungeon game that I'm writing. I'm using this command pattern in my dungeon game as well, and perhaps we'll have time to talk about that in a minute. So we have, but I'm using the example from the book here, and we have an excellent example in the book. And the example in the book uses a kind of a pretend remote control object. Let me get a laser pointer up here. A pretend remote control object, and this is like a multi-device control. And here we have on and off buttons. And then in here, what would be displayed over here might be TV, Bluetooth player, you know, whatever it is. These are the devices that you want to control. It might be the living room light or the ceiling fan or the fireplace, whatever it is. And you're going to basically, quote unquote, program this so that the on and the off switch here work on whatever device is in here. And so that's kind of what all this describes to you. And what we've got is a kind of an interesting situation, because every one of the devices that we can put in here is going to be different. It's going to have its own code. That's what we have right here. All of the vendors, you know, the lights, the ceiling fans, the television, the stereo, the faucet control, the hot tub, the thermostat, security control, they all wrote their own code. And so it's a problem because the person who is making the person who's making the remote control now has to have this huge amount of knowledge about all these guys. He has to know how to call the different methods in every different class. And so two problems come up with that. First, it really makes for a complicated garbage looking piece of code that can figure out which object is in which switch and then call that object's correct method. That's the first problem. And the second one is every time we want to add another, oh boy, another kind of object that our remote control can control, we are going to have to go in and change that big switch statement that maybe goes through all the place. And so this looks like it could be a situation. What we're trying to do is we're trying to separate the concerns. And when we say separation of concerns, we have two main things here. One is I want to hit the switch and do something in a class. And the other is my class is going to be unique to a specific object. But I don't want these two things to be overly bound. I don't want them to be tightly coupled with each other. What I want is the remote should know how to make requests to an object. That's one concern. And then the object should be able to control the device. That's a different concern. And if we don't do this right, what we're going to end up with is this very, very complicated switch statement. And that's down here in the bottom. The switch statement would compare the slot's assigned device to a set of options. When it found the right one, it could call the right methods. And quite frankly, this just looks absolutely hideous. Every time a new device comes out, we're going to have to change that device. Ugh, we don't want that. That's what we've got here is we've got a situation where we are exposing ourselves to control. So remember, our principle is we want to identify the things that change and try to encapsulate them. And so this principle comes in here on the command object. See how in just a second. So we're going to bring the command pattern in, and it's going to help us here immensely. What the command pattern is going to do is it's going to allow us to decouple the request of an action from the object that actually performs the action. And if you'll recall on the previous slide, that's exactly what we need. We have a push button action, and that's supposed to bring about an action in a subclass. And then the action in the subclass is supposed to control some unique device. And what we'd like to do is separate those concerns. And the command pattern allows us to do just that. So in our situation, the one thing that will change the devices and the device assignments is right in the middle. But let's encapsulate. Let's see how we can do it. So what we're going to do is we're going to have what's called a command object. And you will, I think, see in just a minute how wonderful and magical this is. A command object will encapsulate the unique code to do something like turning on a light or dimming the light. And it will encapsulate it under a single common interface so that every piece of code that we have that controls the TV or the stereo or the hot tub is going to be now encapsulated under an interface that gives us a single command to execute the unique code that's inside. And when we do that, we're going to basically be putting a generic interface in front of our action objects. So the command objects will have a single interface that can be used and executed by the commander. In our situation, the commander is the remote control or the person pressing the button. The command object is going to have a single method in its interface called execute. And it's inside this execute method that we will place the light object or we will place the TV object. And this inside the execute method is where we will do the unique code. The remote control won't have to know anything about what's inside the execute code. He'll simply know, hey, I have a command object and I call his execute method and I don't worry about anything else. And this is going to decouple the code inside the command object from the knowledge that the remote control has. So when we place this common execution interface in place, we're going to essentially encapsulate the different kinds of objects, and that's the part that can change. Now, if you'll notice, this is another one of our principles right here. I'm going to draw on this guy, I think, right here. We're going to be programming to an interface when we do this. And that is one of our key principles as well. So you can see we're encapsulating what changes. We're going to be programming interface. So the Head First Patterns book gives a really nice example, sort of an analogy or a metaphor, if you will. And I want to include it here just to make sure that you're kind of getting the idea of what the command does. Now here's a situation where, let me get my marker up here. And you are a customer at a restaurant. I think this is supposed to look like Steve Jobs or something like that. And the waitress is the connection between you and the cook. And you give your waitress your order. I want a hamburger, fries, chocolate shake, no pickles, and you give your specifics to the waitress. The waitress writes it down on an order slip. Oops. And on the order slip, she has put what you want. Make a burger, make a shake. But the order slip has just one thing. It's just an order up method. And so what she then does is she walks over to the cook and says, hey, order up. She doesn't tell the cook, cook a hamburger, cook a shake, cook some French fries. She just says order up. And so what she has done is she has separated your complex order and been able to deliver it with a single command. And that's what's going to happen in the command pattern. So she has the ability to invoke the order up method, and you can kind of see it on the slip there. And throughout the day, every time she takes an order, she writes down the unique things, but she encapsulates it inside an order up request. And so all she has to do is say order up, and then the cook takes what's inside the order up method and executes it. Now, in our example, the waitress is decoupled from the cook. She doesn't have to know anything about what she's doing. She just says order up. And so how do we relate this to the remote control? The remote control has to be separated from the code that's unique to a specific device. When we push the button on the remote control, we don't want it to have to go through a bunch of if statements or a big switch statement to figure out which device we have in the slot, we would like it to just be able to say, execute the code that is inside that slot. And so we're going to create an object that has an interface that has an execute method, and inside the execute method we'll put the specific code. Now down at the bottom here, get a laser pointer back, down at the bottom here is where we can actually see the interface that we're going to create. Very simple interface, and that's one of the beauty about so many of these patterns is that so many of these patterns have a very, very simple underlying architecture, which again makes them elegant and gives us a great example for how to write this kind of code. The public interface command is going to simply say, hey, if you are a command object, you're going to have the execute method. So every command object will have the execute method. What does that do for our remote control? Our remote control doesn't have to know anything anymore. It's just going to be given an object that it can say execute. Inside the execute method, we will of course have unique items. And so here's what happens in the light on command object. Now this is a command object, and it's an object that's going to turn the light on. And so I'm right down here in the, let me get the, you can't see where my mouse is, so let me get the, I want to use black here. There we go. So our light on command object, this is an object that's going to turn the light on. And it's going to implement the command interface, which means it has to have an execute method inside of it. All right? But it also has to have something else. It has to have the actual code that's going to turn the light on or off. And so the command object is this guy right here. The light object is up here, and the light object has two very simple methods, on and off. And so what happens when we run the constructor for the light on command? Well, we hand it a light object, and this light object will be bound to a specific light in our house, and that's what this one is. So this object, its light, will be bound to the specific light object that goes to the light we want the remote control. Now, when someone presses the on button on the remote control is going to call the execute method. That's all it has to worry about. It doesn't know any more than that. But inside the execute method, here's where we have some specific knowledge. This knowledge is separated from the remote control. The remote control only knows about the execute method right here. But the execute method here says, hey, I've got a light object. I'm going to turn the light on. So it calls the light.on method. And so this unique code has now been separated from the remote control. The remote control had no idea that this code was run. The remote control simply had to run the execute code. Very nice. Now, how do we make this work inside the remote control class? Here's our simple remote. Now, this one is a simple remote control. In your Head First book, you'll see one that has multiple slots, but this gets the idea, I think, across very well. First of all, we have a command slot, and this is where we're going to drop our command object. See, this is a command object, and it's one of the slots on our remote control. And this is our constructor for the simple remote control, and nothing happens in it. Now we have a set command method. This is a classic setter, and we're going to pass it a command object. Remember in the previous slide, we saw the creation of the command object. And so we simply say, hey, this slot is assigned this command object. It's set. Now we have a button press method, and the button press method says slot.execute. Why can we do that? Because the command object always implements the command interface, which contains this execute. Now, does the remote control know anything about what's inside this execute method? It does not, and that's the beauty of it. We could just as easily have handed this thing a light or a fan or a hot tub command object, and it doesn't know anything about what's inside. It simply says, hey, when you press the button on this slot, that slot is connected to this command object that you gave me. I call that command object's execute, and after that I have no idea what's going on, which is absolutely beautiful. We can now create as many command objects as we want and polymorphically put them into the slots. It's a beautiful thing. So here's the definition of the command pattern. In the command pattern, you encapsulate a request as an object, and you saw that already. Let me get that that back, and we'll maybe use something a little brighter here. We'll go with green this time. Here is our command object. The command object is the object that has the unique execute method, and that execute method is kind of a generic method. Everything that can receive a command object knows that they can call the execute method. Now, the receiver here, this always confused me. I really didn't like the word receiver here, but the receiver is the bit of code that receives the execute command and runs its own unique code. And this is, as you can see here, encapsulated inside the command object. So whatever kind of receiver object I'm given, I'm going to do its actions inside the execute. The execute method knows what kind of receiver it has, calls those actions, because the execute method has knowledge about that. The outside device, like the remote control, doesn't know what's inside the execute. It just knows it has a command object and it can call that execute method. So what are we talking about here then? We're talking about the idea of parameterizing objects with different requests. What does that mean? When we parameterize something, we say, I'm going to turn it into an object that I can pass as a parameter inside of a function call. So the example of the remote control is kind of a static thing here. We're going to put different command objects inside the different slots. But you could just as easily see a situation where you have a processor that can set up a queue of command objects, and so other devices, other processes, other threads put command objects in this command queue, and the processor simply takes the first command object off of the queue and runs its execute method. The processor has no idea what's in the execute method, and now you can have all kinds of different jobs put in a single queue, each one inside of a command object. And that's pretty nice. That gives us a lot of power. What about if we kept those previous command objects in another storage place where we said, hey, here's the history of the objects we had? Then you could implement an undo, because if somebody wanted to undo, they could simply go to the last object that they just ran, and you could have an undo method in there that would undo the work that was done inside there. And again, the processor would have no idea what was going on. So when we parameterize something, I'm going to see if I can clear this. Do I have an eraser? Yep. There we go. When we parameterize something, what we are doing is we are saying, I'm going to take my code and bury it in an object with a single interface. And now that object can be passed as a parameter to anything. It could be passed to a remote control and put in a slot. It could be passed as a set of actions that need to be done in a queue, and you could order the actions in whatever order you want because they're just generic command objects. I'm going to go back to my little dungeon program again. And I'm partially mentioning this because I want you to see that I use this stuff in my programming today, and it makes my program so much easier. So inside each of those rooms, the player could be inside of a room, and there are 3 doors. And each door, there are a number of actions that can happen inside the room. For instance, there could be a resident in the room, like a wise man who helps the player get stronger or quicker, or there could be a magic item in the room, or there could be a monster in the room. And so each different kind of resident that's in the room has different actions with the players. But I didn't want to have to write a bunch of code that created a big if statement to say, if there's a magic item, do this. If there's a monster, do this. So what I did was I used the command pattern, and I buried the code for magic items and monsters and merchants and everything inside the command object, and my room has no idea actually what's inside. He just is given the room that the player is in. It simply has a command object, and if the player tries to interact with whatever's inside the room calls the execute method on the command object, and then the object takes over and interacts with the player. What this did for me was it allowed me to simplify my code inside the room by decoupling the request of the player to click on and interact with whatever he sees on the screen with the actual code that's going to handle that. And my room code is extremely simple as a result. As you might imagine, if I sense a click in a particular region, I simply call the command object for that region. And then what I was also able to do was I was able to write command objects for each individual door, so that if you click on a door, I again call the execute code for that door, and that door can do something unique. The room doesn't have to know anything about what that door is going to do because the door has its own hidden code underneath the command interface. It's really, really quite nice. All right, so here's the light UML for this thing. And let me grab a red marker again. We're going to start up here with the invoker. This is the remote control, or in my dungeon game, it's the room, or the sensing of a mouse click on a specific part of the screen. And so what the invoker is going to do is it's going to have a command object, and that's the end of what it knows. If it's asked to run a command, it's going to call the execute method on the command. It does have a setter so that we can hand it a specific command object, but that's the end of it. And so our invoker is really simple. Here's the interface. We don't actually implement the interface in hard code. We implement the interface in specific command objects, and every concrete command object has an execute method. What does the execute method do? Why, it calls our execute method, and what we're going to do is this receiver, again, I'm not real fancy about the receiver, the word receiver, but I understand what it's trying to do. This is the thing that handles the actual action. And so we give a receiver to the command object, and the receiver's actions are buried inside the execute method. So the remote control up here calls the execute method, but has no idea what the receiver is. The receiver itself can then do specific things with a specific client. All right, and hopefully you can see how beautiful and elegant this is. I'm going to clear this. You can actually see the picture again. And this is the UML that you would be looking for if you were looking for a command object. All right. All right, so that's it for the command object. If you have any questions on that, please go ahead and give me an email or talk to me in my office. This week, though, I think you're going to have to email me because the homework is due before we'll be back on campus. All right, so now let's talk about the last three patterns. They're all related to each other. And just hang in there. We'll probably be done in about 20 minutes on this lecture. And the last three patterns are the adapter and the facade and the, had it just a second ago. We'll see it in a second. Forgive me for that. All right, so in the decorator pattern, we created an object that was an interface that allowed us to wrap a base object inside another base object. We had, like, in the program you wrote, there were Disney tickets that then were decorated with park hoppers or other kinds of features. And in the example in the book, it was coffee, that did that. So what we're going to do here is we're going to do something a little bit different. It's going to be similar, but it's different. What we want to do is we want to create a situation where we can allow one code to work with another bit of code that they weren't necessarily intended to talk to each other. And so we're going to create what's called an adapter class. And as soon as you see it, you'll say, oh, this is very obvious. But it's a beautiful pattern, and it's a powerful one. When I went to Europe, I had to purchase an adapter because all my electronics were built on the North American power outlet. And so I simply purchased a multi-country adapter that allowed me to plug my plug into the adapter, which then would fit into the plug of whatever country I was visiting. And so that's very powerful. This is exactly what we're going to do with the adapter pattern. So here's one system over here on the left that has a particular triangle interface. And here's the vendor class. We'd like to buy this vendor class from somebody because it has some powerful features, but its interface is round like this, and these two interfaces don't talk to each other. So this is where we're going to put the adapter class, and it's going to look like this. And you say, well, duh. I know. I mean, it's really simple, really obvious. The adapter class is going to go in the middle. It's going to match the interface from the existing system. It'll have the right calls that this guy wants to make. It will translate them and reword them and then make the calls over to the vendor class. The adapter class doesn't actually do much. It simply translates. It's very much from, I'm going to go from German to Farsi, or I'm going to go from English to Chinese, and then when the stuff comes back, I'm going to repackage it, and give it back. So it's, in a way, you can almost think of it as kind of a translator. And this is going to be used when you have a system that you don't want to change and you want to use another system that you cannot change, or the other way around. You have a system that you cannot change and you want to use a system that you have written. And all you're going to do is you're going to write this piece of code that goes in the middle. Now, what are we doing when we do this? We are going to be encapsulating the change in this adapter we're going to be after. So let's make a turkey work like a duck. Here's our duck class from the duck simulator program, and we have a mallard duck, which implements the duck interface, and there's our quack and our fly, and great, everything is looking really good. But now we'd like to implement a turkey. Here's a turkey class. The turkey has a gobble and a fly method. Obviously, it doesn't work right because we want a quack and a fly method. And so here's our gobble method down here. And we cannot call the turkey object because it doesn't have the right interfaces. So let's wrap it in an adapter class, or put an adapter class in place. And here it is. Here's our turkey adapter. Our turkey adapter implements duck and has a turkey. All right, so here's composition in play. We're going to implement the duck interface, program to that duck interface. We're going to use composition. Has-a is preferred over is-a. And here's our turkey adapter. This is the class that we're in the middle of. And we simply, when we instantiate it, we hand it a turkey. Turkey 5, for instance. Now, our duck class uses a quack method. And when our duck simulator calls the quack method will simply call the turkey's gobble method. And so this is translating the quack request into a gobble request. Now, the way turkeys fly is a little different than ducks. So when the duck simulator calls the fly method on our turkey adapter, we will call 5 little turkey fly methods. Our turkeys are going to kind of hop 1, 2, 3, 4, 5. And so now the duck method can now, the duck system can now support turkeys because we've written a turkey adapter. And you can see how simple this is. Now, obviously, in a real system, it would be somewhat more complex, but still, this provides this flexibility. So when would you use the adapter? The client code is going to make a request to the adapter by calling a method that it already knows. The adapter is going to translate it and then call the underlying object's appropriate methods. Then whatever work is going to be returned will be formatted properly and built properly so that it gets returned to the original client. And here the original client has no idea that the adapter was in the middle. It thinks it's talking to an actual client that it wants to talk to. And this gives us loose coupling. And the reason it's giving us loose coupling is because we have not tightly bound the actual user from the actual vendor code. Instead, we've separated them by putting this object in the middle that gives us a clean. All right, so here's the UML for the adapter pattern. And we have let me get this laser pointer. We have a client, and the client knows that it can talk to, in our example earlier, a duck interface. And so we've got a client that loads a duck, but the adapter down here is implementing that interface. So our turkey adapter implemented the duck interface so that all the duck calls were here. The client made duck calls to the adapter. The adapter knows about the adaptee, in our case the turkey, and it can make the calls to the turkey. So this is your UML for the adapter pattern. So there are 2 kinds of adapters. One of them is a object adapter, where you create an object which implements the adapter. The other is a class adapter, and this is where you design classes that implement 2 different interfaces. And what we're looking at right here is a class adapter. Let me get my laser pointer out here. This adapter interface inherits from the adaptee and the target. And when it's doing that, what we're saying is this thing is going to implement all the methods from both of these guys. It's going to be a target and an adaptee at the same time, so that our client, which will be talking to the target class, will actually be talking to this adapter down here, which implements all the target's methods. And this guy will also have all these methods implemented so he can do the translation. Let's look at a pro slide here, or a comparison and contrast. The object adapter uses composition. Now you may remember one of our principles from week 1 was favor composition over inheritance. And even in these two, the book is very egalitarian about this, and I appreciate that. I don't want to be religious about this, but I actually prefer the object adapter over here to the class adapter, because the class adapter is a relationship, and the object adapter has a relationship, and I prefer to work with has a relationships as much as I can. So let's look at the object adapter. This is the one we actually saw code for with the turkey adapter. It uses composition. We have an interface that has a turkey inside it, whereas the class adapter is inheriting from two different base classes at the same time. The advantage here is you don't have to write the base class's code. You inherit all the base class code, and so you don't have to rewrite it. That means it's considered more efficient, as you can see in the second box here under class adapter. Let me get that laser pointer up right here. Now you'll notice I've got a note here that I would rather be flexible. The object adapter, which has a relationship, can be more flexible, and I prefer that. I find that when I'm writing code, that composition buys me a lot, and multiple inheritance to me makes things more complicated. And so if you're in the object adapter, any behavior that we add will work with all the subclasses. But in the class adapter, if a subclass of the adaptee, in other words, if a subclass of the turkey class adds a code object, then we're going to have problems because we'll now have to compose the subclass. You see, it gets more complicated when we use a class adapter. So I tend to prefer the object adapter between these two, although your mileage may vary, and I'm certainly not saying that it's always going to be right in one situation or the other. You need to understand both of these and just pay very close attention if you which one you want to develop. So there's also one more. This is our final pattern here for today. You guys have done a great job hanging with me. I appreciate that. About 47 minutes into this lecture. All right, so that's called the facade. Imagine a situation where you have a bunch of different kinds of classes, and they all control each a different device. And you can see that over here. We've got a projector, a DVD player. This is probably a Blu-ray player in today's books or something like that. An amplifier, a tuner, you know, all these different things, a popcorn popper, and this is also we can watch a movie. Now, if you want to write code that's going to control all this, it's going to be pretty ugly because you're going to have to know about all these interfaces and you're going to be tightly bound to them. What do we want to do? We want to have loose coupling as much as possible. And so that's bad to have this, you know, if we have some sort of master controller up here that tries to talk to all these things. Here's what that code would look like. We'd have to turn the popcorn popper on, tell it to pop the code. We'd have to dim the lights, bring the screen down, turn the projector on. So this is a lot of code, and it's tightly bound to everything that we just saw in the previous picture that I've animated over here. So how do we fix this? We're going to implement a facade, and a facade is exactly what it sounds like. It's a front. A facade pattern tries to take a complex system like the one we just saw and simplify it by providing a single interface. So once again, we have the principle of programming to an interface. It's a very simple interface, and it doesn't prevent the upper level system from going around it into the underlying, so it doesn't encapsulate all the complex classes. It simply simplifies them for the upper level client. And then what we're also doing is we're encapsulating changes in the facade without hiding the underlying architecture. The big win that we've done is we've been able to separate the underlying architecture from clients up above. They now have a simple interface to call to get things done, and that decouples them, which in a way encapsulates some of the change. And this is similar to the adapter pattern, but the intent is very different. So it's very important that you get this. I want to get my laser pointer back out here. The intent of the adapter pattern is to alter an interface to use something that was previously unusable. So the intent of the adapter pattern is to, if in a way, be a communicator or a translator between two objects that don't work together. In the facade, it's not that we have two objects that don't work together, it's that we have a really complicated system underneath and we want to simplify it. So the adapter translates between two objects and the facade simplifies between one object and a complex set of objects. I hope that was clear. All right, so the definition of a facade and the principle of least knowledge. This is one of our new principles that you have to learn. The facade pattern provides a unique interface to a set of interfaces in a subsystem. It defines a higher level interface that makes the subsystem easier to use, and the intent of it is what separates it. It's trying to make the subsystem easier to use, all right? Now we have this principle of least knowledge that comes up here. And the reason it comes up is you can sort of imagine where you might have higher level code that calls your facade and asks your facade to call into the lower level code. And if you do that, what you're actually doing is you're actually binding the higher level code through the facade into the lower level code, and this is considered very poor programming. It actually increases the coupling not only to the facade, but also through to the underlying objects. And so in the principle of least knowledge, we have something that says, let me get the pen out here. Talk only to your immediate friends. In this particular method called getTemp, we have a station object, and we ask the station object to get the thermometer. And when we do that, we're returned with a thermometer object, which we then can call the getTemperature on. And we've all written code like this. I know I have many, many times. In fact, in my dungeon game, I recently put this code in. As I was writing it, I was realizing, I got to change this. I can't have it this way. Because what this does is it binds the station code to the getTemperature code. And the solution for this is to go into the station code and provide, if people are going to need to have the temperature, we're actually going to encapsulate this in a getTemperature. I don't think I can write this very well, but I'll try. This would be, we'd have a station, and instead of a getThermometer, the station itself would have a getTemp. Oh, this is really bad. So what we would do is we would say, hey, station, people need to know the temperature, so provide us a getTemp method and encapsulate this thermometer thing so we don't think about it anymore. This is, when we do this, we're actually providing a facade. And so a facade is an example of where we try to reduce the coupling between layers of devices and make sure that our facade provides all the needs that the upper level client has so that the upper level clients do not bind themselves to the lower level clients. Let me get rid of as many of these as I can. All right, very good. All right, you've hung in there really well with me. This has been a 50-minute YouTube lecture. Hopefully you've taken the opportunity to taken advantage of the fact that it's on YouTube and paused it or rewound it or whatever. Good luck to you this week. The homework is due on Sunday night. This is 2023, and so it will be due on March the 19th, I believe. There's also a program due Sunday night. I believe you're going to implement a Singleton for me. There's no quiz this week on March the 13th. Normally we would have had a quiz, but we don't have a quiz. I've simply dropped it. And that means that the total points that you can earn in this course are 230, and you can do the math on what 90% of that's going to be. It'll still work out to be about the same. Please email me if you have any questions, and I look forward to seeing you next week in class. Have a great day.